Alright, so in this lesson I'm going to do an introduction to magnetism and kind of talk about what does magnetism really look like and what do we talk about what do we mean when we talk about magnetism. And so if we look at magnetism in general, magnetism as a property was discovered about 2,500 years ago, at least in the Western world. Where this started to get used, first of all, was realizing that certain types of metals point north-south, and so you can make a compass which really revolutionized, at least for people in Europe, how you go from one place to another over the open ocean. There are other ways to navigate over the open ocean that were used by other cultures in other areas of the world. The Polynesians would be a good example of another one who has another technique that did not depend upon having a magnetic compass. But that's about where magnetism starts to be discovered. We discover that some substances are permanently magnetized on their own. Iron is a great example of one. If you magnetize iron, it remains permanently magnetized, and so that's why we call these ferromagnetic substances. If you go up in northern Minnesota, there are certain rock formations that are magnetized when they were formed thousands and thousands, probably actually millions and millions of years ago, up in northern Minnesota, when the magnetic field of the Earth had a different orientation. What this means is if you try to use a magnetic compass on these rock formations, your magnetic compass doesn't work very well. Some substances are attracted to magnetic objects. We call these paramagnetic. You might have seen like a fridge magnet. The metal that a fridge is made out of is really a paramagnetic metal. It doesn't have a permanent magnetic field in and of its own, but you can induce a magnetic field on it, which allows the objects to be attracted. And then some substances are repelled by magnetic fields. And so if you apply a magnetic field to this substance, it induces a magnetic field in a way that the objects repel from one another. Magnets always have two poles. We call them north and south. Opposite poles attract, like poles repel. Kind of similar to electricity in that way that opposites attract, likes repel. If you take a magnet and cut it in half, those two magnets both have north and south poles. If you cut those magnets in half, you have four magnets, all four with north and south poles. Then it doesn't matter how much you cut a magnet in half, that you always have a north and south pole. This is important because it means that magnets are always found in dipoles. There's always a north and a south. This is a little different than electricity, which you can find what we would call a monopole, all positive, all negative. Where in magnetism, as far as we know, magnetic monopoles, a north or something that's all north or all south doesn't exist. The magnet always exists in a dipole formation. So magnetic field strength, we give this the symbol B. I'm not really 100% sure why the symbol B is used. Probably can guess why M is not used. You have mass, and so we don't want to get confused. It's a vector that we define pointing from the North Pole to the South Pole. The units of magnetic field are the Tesla, named after Nikolai Tesla. The magnetic field of the Earth, probably one of the magnetic fields that we are in contact with most frequently, is anywhere between 25 microtesla and 65 microtesla, depending upon where you're at on the Earth's surface. If you're closer to the north or south magnetic poles, that strength gets a little bit larger. If you're further from the north and south magnetic poles, that strength gets a little bit weaker. You can actually look at areas and see where they're at in terms of latitude by looking at the strength of the magnetic field. So if we look at in Faribault, Minnesota, the average magnetic field strength here is about 55 microtesla. If we look at something like Beijing, China, 54 microtesla. We have magnetic fields that are about the same strength here in Beijing. Even if we go to Seoul, South Korea, about the same strength. If you go further south to someplace like Bangkok, Thailand, you have a much weaker magnetic field in that location. Now, the Earth's magnetic field, the North Magnetic Pole is not at the geographic North Pole of the Earth. The North Magnetic Pole is actually offset a little bit. And we'll talk about that here in a little bit, why that is. So the North Magnetic Pole and the North Pole are not at the same location. If you're using a magnetic compass and you've actually done something called orienteering, you might have heard a term declination, which talks about how far does your compass point from actual north because of the separation between the North Pole and the North Magnetic Pole of the Earth. So the Earth has a magnetic field. It does act like a magnet. What this is really caused by, or at least our best guess, is that there are electric currents in the molten iron in our planet's core. This is not a static field. It actually is always changing, is changing in strength, but it can also change in polarity. If you go and look at rock formations of ferromagnetic rocks that have been formed over different periods of time, probably the best place to look for this is if you go in the Atlantic Trench, where the two plates that make the Atlantic Ocean are separating. You have a series of rocks, basically iron, that has come up through the Earth that have cooled over different periods of time. And what we see is that the Earth's magnetic field has varied in orientation several times over the last 100,000 years. Now, what would happen if the magnetic field decided to switch polarity on us? I'm not really sure. It might not be very good for us, mainly because all of the electrical devices we have might be damaged or destroyed. But we know the Earth's magnetic field is changing. It's not a static field. There are other objects that we know have magnetic fields. The moon is a magnetic field. It's about a thousandth the strength of the Earth's magnetic field. Most of the planets have magnetic fields. Jupiter has probably the strongest magnetic field of any planet, about 20,000 times that of the Earth. Venus and Mars, oddly, do not have magnetic fields. We'll talk about why that's important here in a bit, at least for traveling and living on Mars, why that's an important fact. What this tells us about Venus and Mars is we believe that the cores of those planets are no longer molten, but rather solid cores. The reason why they wouldn't have a magnetic field, there's no electric current in that solid core anymore. The Sun is probably the strongest magnetic field in our solar system of naturally occurring magnetic fields. We know the Sun has a magnetic field that the poles reverse about every 11 years. This is actually related to sunspots, the formation of sunspots and solar flares. There's a cycle of sunspots being formed in greater frequency versus lesser frequency that has a period of about 11 years. That's related to the period of the reversal of the polarity of the Sun's magnetic field. So why is it important that we have a magnetic field where something like Mars does not have a magnetic field? Well, our Sun, if we actually look at what our Sun is doing, it is a gigantic furnace where there's nuclear fusion going on inside the furnace. It's bombarding all these particles together at very high temperatures and very high energies. What starts to happen if you bombard particles together with very high temperatures and very high energies is other particles get formed and you break atoms apart. Some of these other particles are alpha and beta particles. Both those are types of what we would generally consider to be radiation. More specifically, they're ionizing radiation. An alpha particle is essentially a helium nucleus. A beta particle is essentially an electron. Protons get thrown off of the Sun. There's actually, you can measure the number of protons that come off the Sun. And there's also other more exotic particles. If you look at types of subatomic particles that can be formed in high-speed collisions, you get some weird stuff that gets formed. Basically, a lot of these particles, what they do when they interact with your body is they ionize atoms they come in contact with. The reason why that's not necessarily good for your body is if you have something like a strand of DNA, your DNA is held together by hydrogen bonds, basically small electrical attractions between molecules. If you start to do something like ionize one of the atoms in that molecule, you can actually get things that don't fit together very well anymore. And so these types of ionizing radiation, depending upon which atom they strike and where they strike that atom in your body, can be pretty much benign, or they could be something that's very dangerous. When we talk about mutations to your DNA, this is one way that mutations occur when you have radiation changing the structure, either changing what atoms are in a molecule or changing how those molecules fit together. So what the magnetic field of the Earth does is it puts a force on moving charged particles. These are charged particles. They're moving really fast because they're getting shot out of the Sun at a high rate of speed, and so they actually experience fairly large forces. And so one of two things happens because of our magnetic field. Either these charged particles get absorbed, captured, and then in our upper atmosphere near our two poles. If you've ever seen the northern lights, essentially what you have is a large amount of this type of radiation getting absorbed in the upper atmosphere. What the different colors are different atoms, different molecules of gas that are absorbing those particles and then giving off light that we see. Something like green, which is a normal color, is related to the emission spectrum of nitrogen. Since nitrogen is the most common gas in our atmosphere, it'd be pretty common that would be green. Happens to work out there's a phenomenon in the southern hemisphere called the southern lights, which is the exact same phenomenon as the northern lights. The other thing that could happen is that the force could deflect these charged particles away from the Earth out into space somewhere. So essentially what the magnetic field of the Earth does that's important to us is it protects us from all sorts of radiation that we normally wouldn't be protected from. So if you do something like go to the International Space Station, there's a lot of radiation you're not protected from at the International Space Station that you are protected from here on Earth. If you were to do something like go to Mars, there'd be a whole bunch of radiation that you're protected from here on Earth that you would be exposed to both on the trip from here to Mars, but the entire time you're on Mars. So I think one of the challenges with sending people from here to Mars is how do we deal with all of this radiation, which probably is unsafe for the type of exposure you would have to that radiation over the time period it would take just to fly to Mars and back. So the other thing to kind of look at is when we looked at electric fields, you have electric field lines. We can draw the same thing for magnetic field lines, showing how the magnetic field looks. Here I have what we call a bar magnet, a north pole and a south pole. And what you see is you can follow any one of these lines and trace it from north to south. And this is actually, you can do this by just taking a bar magnet and having some iron filings. Ask me to do this demo in class. It's a pretty easy demo to do and pretty cool to see what the magnetic field lines really look like. So that's a quick introduction to magnetic fields and maybe why they're kind of important to us. We'll look at in the next lesson is when we talked about moving charged particles experience a force due to a magnetic field. We'll start to look at what does that actually mean and how do we define that force.